Yeah, good morning, students. Sorry for the delay. Today we'll see the last part of the module 5. Maybe in the next 30 to 40 minutes, we'll try to cover the last part of this module 5, and that will be the end of the digital part of your syllabus, because you know the subject title says analog and digital electronics. So we have not covered the analog part. We are ending today the digital part, and maybe in the next class we'll be starting with the module 1 and we'll be discussing the analog part, right? So today we are going to discuss about the two important concepts in this module 5, and those are the sequential parity checker and the serial adder. I hope already you people might have done one experiment in your laboratory for the parity checker, but that parity checker what you have implemented is the combinational parity checker. But here we are going to discuss about what is called as sequential parity checker, and one more thing we are going to discuss about the serial adder. So far we have discussed about a parallel adder also. So already we have discussed about the parallel adder, and we have seen how multi-bit numbers can be added using series of full adders. And in fact, we have discussed that parallel adder with accumulator in this chapter itself when we discussed about the register. So can anybody tell me what is parity checker? Before we discuss about the sequential parity checker, can anybody define what do you mean by parity? And then what is parity checker? And then we'll see what is sequential parity checker. So can anybody define what is parity? Yes? Anyone? Can you tell me what do you mean by a parity? Yes? Yes, Madhura, what do you mean by parity? Yes? Are you there, Madhura?
Yes, sir.
What is parity? What exactly you mean by parity bit, or what is parity? And then what is parity checker? Yes? Abhay?
Yes,
I hope all of you have done the experiment, parity checker in your lab. Yes or no? Yes, Abhay? What is parity and what is parity checker? See, no answers. Ritika? See, when the question is asked, nobody will be there to tell the answer. Anyhow, I will start with what exactly you mean by parity checker and what is sequential parity checker. Okay, we'll start with this. A sequential parity checker. Is the screen visible? Yes?
Yes, sir.
Okay.
Yes, sir.
So what exactly you mean by parity bit? Normally, when you transmit the data, right, when you are transmitting data from one point to another point, that is from sender to receiver, in order to detect whether the received data is error free or is there any error, we use one extra bit attached to the actual data bits, and that extra bit which we attach to the actual data bits is called as a parity bit. So based on what parity we want, we will be attaching one extra parity bit, and that parity bit could be either 0 or 1 depending on which parity you want. And this parity bit helps us to detect the error at the receiver when the data is received from the transmitter. For example, here I have shown a 7-bit data, and the 8th bit which we have added here is called as a parity bit. Now you can see that the first 7-bit number, if you see here, is all zeros. To that I have added 1 as the parity bit, right? So before we see why you have to add 1 or 0, so can anybody tell me what is even parity and odd parity? Omkar, can you tell me the difference between even parity and odd parity? Yes. What exactly you mean by even parity and odd parity? I have told the extra bit which we are adding is called as a parity bit to the data bits, right? And the parity could be even parity or odd parity. So when you add a parity bit to the data bits, and if the total number of ones in that data plus parity, if the total number of bits are odd, then we can say that that word is having a odd parity. And if the total number of ones is even, then we can say that that word is of even parity. So in this example, we have taken 7-bit data and 1 parity bit. So totally we have 8-bit word. So this 8-bit word is said to be even parity if the total number of ones in that particular word is even. That means if the total number of ones in a 8-bit data are 0, 2, 4, 6, 8, then we can say that it is a even parity word. Similarly, if the word contains odd number of ones, that means the number of ones present are either 1, 3, 5, 7, then we can say that the word is of odd parity. And if any single bit in the 8-bit word is changed from 0 to 1 or from 1 to 0, the parity will change. Like for example, here in this particular case, as I said, I have taken a 7-bit data, right? You can see here we have a 7-bit data, right? And in this 7-bit data, the first data bits are 0, 0, 0, 0, 0, 0, 0. All 7 bits are 0. Correct? So I want to make the parity of the word to be odd. So what I need to add for the first number? Definitely I have to add 1 here. If I add 1 here, then the total number of ones in the first word are 1, which is odd, and I can say that the word is of odd parity. Similarly, if you take the second number, you can see again here how many ones are there in the 7-bit data? Only 1 is there. So already it is a odd parity. So you have to add 0 to retain the odd parity. Similarly, the third number, if you check, number of ones here are 1, 1, 1, 1. That is 4. In 7-bit data, there are 4 ones, which is even. But I want odd parity word. So what I need to add? 1 here. So if you add this 1, now there are 5 ones, and it becomes a odd parity. Similarly, here also there are 4 ones in the data bits, like 10, 10, 101. If you take, there are 4 ones. Still, I want to make it is even parity. So I have to add 1 here. So now the total number of ones will be 5, and it is called as odd parity. Similarly, the last 7-bit number contains 3 ones, which is already odd. So I need not add another one. So I have to add a 0 as a parity bit, so that the total number of ones including the parity bit becomes 3, and it is of odd. So all the numbers 8-bit word here shown, they are of odd parity, right? I hope it is clear. Omkar, you understood what exactly you mean by even parity and odd parity? And here we are taking the example of odd parity. So I have shown all numbers are of odd parity depending on what number of ones are present in your data bits. You have added either 0 or 1, so that the total number of ones in the 8-bit word remains odd, and we can get the odd parity word. Now, you may ask how it helps in detecting the error. You have added already the parity bit, and you know that all the data bits or data words which will be sent from transmitter, and they have to be received at the receiver, compulsory whatever bits we are receiving, they should have odd parity. But by chance if we receive it as even parity, then definitely we can say that there is a single bit error in the data received. This is how the parity helps us to detect the error present in it. So if any single bit in the 8-bit world is changed from 0 to 1 or from 1 to 0, the parity will no longer be odd. Thus, if any single bit error occurs in transmission from transmitter to receiver, with odd parity, the presence of this error can be detected because the number of ones in the word has been changed from odd to even. So when you have prepared an odd parity word, at the receiving end also it should be odd parity only, but by chance if you receive it as even parity, then there is definitely a error. So now we will try to design a sequential parity checker. A sequential parity checker means what? We have to receive a series of data and we have to check that data which we have received is of even parity or odd parity. Since we are going to design here odd parity checker, we need to check whether the received data is even or odd, and if it is odd, we should give the output Z as 1, and if the received data has even parity, then we should make Z equal to 0. So here we are taking X as the input along with the clock and Z is the output. Z equal to 1 indicates the received bits are having odd parity, and Z equal to 0 indicates the received bits are having even parity, or there is an error occurred when we get Z equal to 0. Z equal to 1 indicates the received data is of odd parity. So this is the block diagram I have shown here. Just concentrate on this part first, the block diagram. If you see here in this block diagram, we have taken data input as X, another clock and X are synchronized. So whenever clock is applied, first bit will be appearing at the parity checker, and once you receive the first bit, you have to check whether it is even or odd, and accordingly you have to produce the output as Z. The sequential circuit must remember whether the total number of one inputs received is even or odd. That's why it is called as sequential parity checker. So to design this sequential parity checker, we will consider two states, S0 and S1. S0 is a state of even parity, S1 is a state of odd parity. So whenever the circuit is in S0 state, since it is even parity, the output Z should be 0. And whenever the circuit is in S1 state, it is of odd parity, you should get Z equal to 1. Right. So initially by default, you have received nothing. So 0 number of ones you have received, which can be considered as even. So by default, the parity checker should be initially in the S0 state, giving Z equal to 0. Now we'll see what happens when we receive X input one by one, and whether we will move from S0 to S1. So you can see this state graph now. It is very important and very easy, and easily you can design the sequential parity checker. So whenever the circuit is in state S0, Z equal to 0. And whenever the circuit is in S1, Z equal to 1. Now assume that you are in S0 state, and if you give X equal to 0, if you get X equal to 0 at the input, whether you will remain in S0 state or you will go to S1, because already you are in the even parity state and you have received the next input X is equal to 0. So when you receive X equal to 0, the parity will not change. The parity initially it was even. The circuit remains in the same state S0, giving output Z is equal to 0. But if you are in state S1 and now if you get the input X as 1, what happens? Initially even parity is there. Now you are giving input as X equal to 1. So definitely by adding this 1, the word becomes what? Odd parity. So you will make a jump from the state S0 to S1, and the moment you come to state S1, the output Z will become 1 because it indicates the parity of the received word is odd. Now, when you are in state S1, if you are in state S1 and if you get X equal to 0, input is 0. The moment you get input 0, the parity of the word will not change. So parity remains odd only here. So the circuit remains in the same state, giving Z equal to 1. But when you are in odd state or odd parity state, and if you get X equal to 1, this 1 will cancel that odd parity and it will make it even. So when you are in S1 state and if you get X is equal to 1, you will be moving to what is called as again the even parity state, right? You will be moving to even parity state. Now this is the state graph for the parity checker. I hope you understood the block diagram of the parity checker and how this state graph is drawn. Now from this state graph you can easily design or you can draw the synthesis table and you can get the logic diagram for this parity checker. Okay, so how do we draw this? Now there are two states, S0 and S1. So you can denote this state by 0 and this state can be noted by 1. So that is what is done here. You can see S0, S1, right? So if the present state is S0 and if you get X equal to 0, you remain in what? S0 only. But if you are in S0 and if you get X equal to 1, you will go to S1. Similarly, if you are in S1, if you get X equal to 0, you remain in S1. And if you are in S1 and if you get X equal to 1, you get to S0. This is drawn from this state graph. Whatever the state graph you are having, you can see here. When you are in S0 and if you give X equal to 0, you remain in S0. And when you are in S0 and if you get X equal to 1, you go to S1. Similarly, when you are in S1, if you get X equal to 0, remain in the same state. But if you get X equal to 1, you will move back to the state S0. And that is what is done here. And when you are in state S0, the output will be 0. And when you are in state S1, the output will be 1. Right? Now the same thing we can implement using any of the flip-flop. So we will use here T flip-flop. Not compulsory to use T. You can use D, SR, JK, any flip-flop. But I am using T flip-flop. So these two states I have denoted by 0 and 1 here. Then this will be obviously 0, 1, 1, 0. The same, this part is whatever we have written here. Of course, this part is indicated here in terms of 0 and 1. I have done the state assignment. S0 is denoted by 0. S1 is denoted by 1. And then depending on this S0, S1, S1, S0, we will get this. Now, we have to derive T flip-flop inputs. Right? When Q is 0 and Q plus is 0, what should be T? It is 0. And when Q is 0 and Q plus is 1, obviously T should be 1. 1, 1, no change 0. 1, 0, change toggle. It should be 1. And the output Z will be 0 and 1. So T inputs for X equal to 0, both are 0. And for X equal to 1, T inputs are 1. Right. So we have got this particular synthesis table. Using this now, directly we can draw the logic diagram because no need to use any K-map here because you have only 2 and you have got both the inputs as either 0 or 1 depending on X equal to 0 or X equal to 1. So this is the block diagram. You can see here X and clock are given as input, Q and Q bar are this. So the X can be given directly to T. If X is 0, Q remains 0, and if X is 1, Q will toggle, right? That is the output Z. So this is how we have designed the sequential parity checker. This is the block diagram of the sequential parity checker and the state graph, then the synthesis table, and from this synthesis table, simply we can have one what is called as T flip-flop with the input X given to the T input and the Q output is given to the Z. And the same operation is explained here in this particular the timing diagram. So that is about the sequential parity checker, right? This is again important from your examination point of view, and very simple thing. Just you have to remember what is sequential parity checker, block diagram, then state graph, synthesis table, and the circuit. Circuit is very simple here. Only T flip-flop you need to use, and the same you can draw the timing diagram here, right? What happens when X is 1 and if clock is applied? When clock is applied and X is 1, it toggles. If the output is 0, it becomes 1. Right, and if the input is 0 and when clock is applied, it remains in the previous state, no change state. That is the property of the T flip-flop, and that gives the designing of the sequential parity checker. I hope all of you understood this. Anybody who has not understood, you can ask any doubts if you are having here before I move to the last part, that is sequential serial adder. All of you understood this or no? Ankita? Any doubts? Yes, if anybody is having any doubts, you can ask me before I proceed further for the last part, that is what is called as serial adder. Yes, anybody is having any doubts here? You can ask. All of you understood this or no? At least say you have understood or no, not understood.
Yes, sir.
Any doubts if you are having? Yes. In fact, already I have shared the notes. If you want one more notes, I will be sharing with you people. You can just go through this and you can prepare for your exam for this particular module 5. Okay, if there are no doubts, I presume that you have understood everything or nothing, and with that assumption I will move to the last part of this circuit and last part of this module 5, that is what is called as serial adder, right? Now what exactly you mean by serial adder? Before that, already we have studied about parallel adder, and we have seen that when you want to add two n-bit binary numbers, we need n full adders, right? And simultaneously we can apply both the n-bit numbers to this full adder, and we can get either n-bit or n plus 1 bit sum immediately at the output of the full adder. But as the number of as the value of n increases, the hardware requirement will be more for the parallel adder. So to overcome this difficulty, we are going for the serial adder, but obviously at the cost of a reduction in the speed, because parallel adder is the fastest. The moment you apply the input, you will get the output because you have used so many flip-flops, so many adders. But in serial adder, what we do is we use only one full adder and one flip-flop, right? So obviously the hardware requirement will be less, but the disadvantage here is, since we are adding bit by bit, only 2 bits will be added at the same time. So the time required to complete the add operation will be more, and as a result, this particular like serial adder will be sluggish in operation or slow in operation. So you can see here I have shown one full adder, and one D flip-flop is used to remember the previous output. So initially what we'll be doing is we have to add Xi, Yi and Ci. So X and Y inputs are given to the full adder, and the previous carry output is given as an input to the full adder. So at the beginning what we are doing is Xi, Yi and Ci are given as input to the full adder, and when we apply the clock, we get the output as Si and Ci plus 1. That is, if we give 0, 0, 0, we will get 0 and 0. So at first clock pulse, the first addition will be done, and we get the output in Si, and the carry will be available here at Ci plus 1, and the same carry we are feeding into the D flip-flop, right? Now, next clock pulse when you apply, you will be applying a next number, that is 0, 0, right? And the carry from the previous addition, whatever you get, right? Whatever the carry from the previous addition you have got, first two bits, that is LSB bits, X0 and Y0, you have added, and you got the sum as S0 and carry as C1. Next, you will be giving input as X0 and Y0 and C1, which is the output of this D flip-flop. So in the next clock pulse, that is at the second clock pulse, actual inputs given are X1, Y1 and C1. That will be added by this full adder, and you get the output as S1 and carry as C2, right? Next, again at the next clock pulse, you will be applying the next two bits, that is X2 and Y2. When you give X2 and Y2, we have to add C2 also. Where is that C2? C2 is already in the D flip-flop. That input will be given. So X2, Y2, C2, all three will be added, and you will get what is called as S2 and C3. Like this, at every clock pulse, one set of bits will be added. So if you are adding two n-bit numbers, here you need n clock pulses. So time required to carry out the addition of two n-bit numbers will be n into t, where t is the time period of the clock. So more time is required here to perform the addition of the binary numbers when you are using the serial adder. The same thing if you use the parallel adder, number of full adders you are putting, simultaneously you are giving all the input in one clock pulse, you will get the output. So time required for the parallel adder will be only t seconds, whereas for serial adder, time required will be n into t seconds. So we can say that full adder is faster compared to serial adder, or serial adder takes n times more time than the parallel adder. So in fact, this particular table what we have shown is truth table of the full adder. It is not the truth table of the serial adder. So you can give the inputs one by one and apply the output of the flip-flop as the carry input, and you will go on adding those, and you will get this type of what is called as timing diagram for the serial adder. I want all of you just try to analyze this. What is shown here, you can see here is at the first clock pulse, we are checking what is X1. What is X1 here? That is X0, 1. Y0 is 0, 0. So what you will get? Output S1 will be 1 and this will be 0. Right? This carry 0 will be added at the next time. Here we have 1, 1 and the carry is 0. Right? So that will be added. 1, 1 gives you output as 0 and the carry will be 1. Next time all the 3 will be added again and you will get sum as 0 or 1, and accordingly carry also you will be getting it as 0 or 1, and that's what is shown in this timing diagram for the serial adder. So if you want to write the state graph of this, you just have to concentrate on this. Don't concentrate on this. This is something else. This is not related to this particular serial adder. So serial adder state graph is this. We have two states, S0 and S1. S0 is like sum without carry, and S1 is sum with carry, right? So when you are in this state, sum state with carry, so if you give 0, 0, like if you give the input as 0, 0, the sum will be 0. If you give input as 0, 1, sum will be 1. If you give input as 1, 0, and sum will be 1. But when you are in this state, if you give 1, 1, your sum becomes 0 and carry will be 1. So you will be moving from S0 to S1. Right? Now when you are in S1 state, if you give input as 0 and 1, sum will be 0 because already there is a carry. That carry will be added, sum will become 0, carry will be 1. Similarly, if you give 1, 0, sum will be 0, carry will be 1. And if you give 1, 1, already there is a carry 1. So 1, 1, 1, the sum becomes 1 and carry becomes 1. But if you are in state S1, that is with carry, if you give sum as 0, 0, input as 0, 0, the sum becomes 1, there is no carry, you will go back to the state S0. So that is how we can implement what is called as serial adder, right? So once again I am repeating, in serial adder what we are doing is two multi-bit numbers or n-bit binary numbers we are adding, but not parallelly, not at once. We are adding them bit by bit. So first we will take the LSB bits, we will add, and we will give the sum and the carry. The carry we will take for the next addition. So carry is propagating from one stage to the next stage, and we will be performing addition of two n-bit numbers in n clock pulses. So the total time required to carry out this particular addition will be n into t seconds, right? That is what is about the serial adder, right? I hope you have understood both serial adder as well as what is called as sequential parity checker. With this, we have come almost to the end of this particular module. Just I wanted to tell one more thing which I have forgotten to tell you people. That also I will just explain, and we'll close the discussion on the digital part. And in the next class, we will be moving to what is called as the analog part. Okay, yeah, this already I have told you. Sometimes they will ask, explain the process of what is called as the steps used in constructing the state table. Already I have explained you about the state table, but what are the steps? You can just go through this procedure. The following methods can be used to construct the state table. What is the first? Determine the flip-flop input equations and output equations from the circuit. Then you have to derive the next state equation for each flip-flop using one of the characteristic equation. You know that characteristic equation for D flip-flop is Q equal to D. Characteristic equation for T flip-flop is T XOR Q. Characteristic equation for SR flip-flop is S plus R bar Q, and JK flip-flop is J Q bar plus K bar Q. Using this, you can derive the next state equation. Then plot the next state map for each flip-flop. If you are using more than one flip-flop, you have to derive flip-flop inputs for each of the flip-flop. Then combine these maps to form the state table. Already I have explained, like you have done the same method in designing the counters also. But just I am listing out all the steps, right? So combine all the K maps to form the state table. Such a state table which gives the next state of the flip-flops as a function of their present state circuit is normally called as the transition table. And once you have the transition table, then you can design that particular circuit. So one simple circuit is shown here. Derive the state table for the circuit. This is the more model circuit is given to you. Don't bother about what this circuit does. Like just you have to derive the state table for this. As I said, the first you have to write the flip-flop input equations. So you can see here, this is DA, right? This is DA and DB. DA is what? DA here is what? The input to this flip-flop is X XOR B bar. So DA is X XOR B bar. And what is DB? It is X or A, that is X plus A. And the Z, that is the output, is what? A XOR B. That is the first step. You have to write the flip-flop input equation and the output equation. DA is X XOR B bar, DB is X plus A, and Z is A XOR B. The next state equation for the flip-flops, you have to write A plus is what? X plus B bar. Why? Because for D flip-flop, output is equal to input. So A is nothing but DA. DA is what? X XOR B bar. So A can be written, that is A plus, next state is X XOR B bar. Similarly, B plus is DB, that is B plus is X plus A. So these are inputs, and in D flip-flop, outputs will be equal to input, that is the next state. Then you can have the corresponding maps using these equations. You can have the three variable map XAB, that is, you can get the equations for this A bar, A plus and B plus. And you already have the equation, then we can combine this in this state table. Since there are 4 states AB, there are 2 flip-flops, means it can have 4 states, 0, 0, 0, 1, 1, 0, 1, 1. You can write 0, 0, 0, 1, 1, 1, 1, 0, right? And for x equal to 0, what is the next state? And for x equal to 1, what is the next state you write? And at the same time, you can write. So this table, very easily you can get from these equations. If you use these equations, you will get this table. Now you can translate this in terms of the state, because we are doing a reverse process here. State table and state graph we need to draw. So we got the state table now. You represent this in terms of states. I can write these states as S0, S1, S2, S3, and then you write it will remain in which state, either S0, S1, S2, S3, and what is the output. And using this, now you can draw the state table. You can see the state table for this. The same thing is redrawn here, and you can have S0 output is 0, S1 output is 1, S2 output is 0, S3 output is 1. And then based on the x, you can see when you are in S0 state, if x is 0, it will go to S3. And if x is 1, it will go to x1. It is shown here, right? Similarly, when you are in S1, you will go either to S0 or to S2. If you are in S2, you will remain in S2 or you will go to S1. It is shown here, S1 or S2. And if you are in S3, you will go to S2 or you will go to S1. This is what is called as the state graph. So if they ask, if they give the circuit, normally from the state table, state graph, we get the state table, we get the equation, and you will draw the logic diagram. But if they ask the reverse way, like in this particular example, they have given you the logic circuit and they have asked you to determine state table and state graph. You can do this. For that, you need to follow this particular procedure which is mentioned here. Determine flip-flop input equation, output equation, derive the next state equation using this flip-flop characteristic equation, use K-map, combine all, and you will get what is called as a state transition table. From that, you can draw the state graph. So that is how we can have the reverse way from the circuit, we can get the state table also. So with this, we have covered all the things that we should supposed to cover in this module 5. If you have any difficulties, any doubts, you can ask. Otherwise, it is the end of the digital part. As the title of your subject says, Analog and Digital Electronics. In the next class, I will be starting with the analog part, that is the module 1. Only one module in which, in fact, most of the things already you have studied. We are going to discuss about that module 1 in the next class. So before I close, if you have any difficulties, you can ask me.